Okay, good afternoon everyone. It is 2:40 in the PM. We are looking at induced EMF from a changing flux. Faraday's law. EMF stands for electromotive force. The name is misleading because in year 12 it refers to electric potential difference. Potential difference is measured in volts, joules per coulomb. When we talk about work being done on charged particles by an electric field, we say that the work done on the charged particle is equal to voltage multiplied by the charge of the particle. So therefore, voltage is equal to work done divided by charge, which gives us the equivalence of 1 volt being equal to 1 joule per coulomb. When we start looking at Faraday's law, or rather when we start thinking about EMF across a current carrying conductor, we have already identified that if you thrust a magnet down into a coil, you'll get an EMF across the coil. We figured that bit out. We have talked about the fact that if you take a straight conductor and whip it perpendicularly across a magnetic field, there'll be an EMF across that conductor of wire. And we have said that the EMF in that conductor of wire, we've said previously, in simplest terms is equal to VBL, where you've got little v being the velocity of the conductor as it moves across the field, capital B being the field strength in Tesla, and L being the actual length of wire immersed in the magnetic field as it goes across. That equation VBL does depend on everything being perpendicular, nice and uniform as well. The strength of the EMF is proportional to the strength of the magnetic field, the speed of the conductor, and the length of the conductor. If you were to connect those ends of that conductor by some sort of wire and maybe put a globe in between, you would get yourself a current flowing. When you do take a rod and pass it across a magnetic field, you'll get a voltage. You won't get a current until you connect the ends. Without connecting the ends, you'll create a voltage in that conductor, but no current. Because just as we see that the electrons will be forced in one direction, then positive charge will equally be forced in the other direction, and those movements of charges cancel each other out. Now, I am not saying that the moving positive charge is moving protons. I'm saying it's moving positive charge. Charge can move without being attached to a massed object. In the case of negative charge, it's usually attached to the massed object of the electron, but positive charge can move simply by the fact that as you look along the strip of material, there are holes which represent lack of electrons moving across the strip of the material. We did see in a previous lesson that the equations voltage equals VBL can be linked to the equation force equals QVB. Okay, so looking at those equations there, that derivation is going from the force on a charge due to a magnetic field and moving through that and deriving the voltage across a current carrying conductor. How do we get there? We know that the force on a charged particle in a magnetic field is equal to QVB. We know that. All right, hold that in your thought. Just lock it in. Now move away from that and go look at the work equation. The work equation tells us that work is equal to force times distance. We learnt that in year 10. So work is equal to force times distance. Now in the case of that charged particle, the force is equal to QVB. So let's plug that in. Let's take the capital F out and we'll plug in the QVB. So now the work done on that charged particle that's moving through a conductor, the work done is equal to QVB multiplied by the length of the conductor. Well, work divided by Q is equal to voltage, is equal to VBL, the equation that we're working with at the moment. So the voltage across a conductor as it cuts across magnetic field, if everything is perpendicular to everything else, the field is uniform, the velocity is constant, the voltage across that conductor is equal to VBL. So velocity is defined, as you know, by displacement divided by time. So we've just chucked that in there. Okay. Now have a look at the numerator in that equation. So displacement multiplied by length of the wire and the distance that it traveled across the field. Here is my length of my wire. Here is my distance traveled. This multiplied by that is the area. And so we have suddenly EMF is equal to B multiplied by area divided by time. And that gives us Faraday's law. Now, when you look at Faraday's law, I think in your formula and data sheet, you are going to see the following. There is always a little negative sign there. That doesn't matter a tremendous amount to us in year 12. It will be quite significant when you go and study electromagnetism, electrical engineering at university. For us, it doesn't matter at the moment. What that negative sign does for us in year 12 is it is an introduction, or it is a warning about something called Lenz's law. The negative sign emerges because we're dealing with vector quantities. It assists in the determination of current direction, which is covered later on. EMF across a coil of n number of turns, therefore, is equal to negative n delta phi on delta t, Faraday's law.